Hey there, it's Dave again with OC Astronomy. And this week we are looking at Chapter 6 in the Openstax Astronomy textbook. If you're here as one of my students, please leave a comment down below. Let me know if this is useful. I also have seen a number of new subscribers on this channel, and so I appreciate that. Those of you out on the internet land, hello, and I really do appreciate the fact that you subscribed. I hope that the information that I give you is useful, entertaining, something. At least you can turn on this channel to laugh at me. But as long as you do, hit the like button and let me know that I'm doing an okay job. I'd appreciate it. So Chapter 6 in Openstax Astronomy looks at telescopes and the ways that we look at light and the instruments that we use. The ancient observatories, El Coracal, for example, and I'll roll in some footage here. This is an ancient observatory, El Coracal, in Chichen Itza. It was built by the Maya, and primarily it was built to observe the planets, especially Venus. These doorways and windows were where they could line up visually and reference where Venus should be and where the sun should be during different parts of the year. Its dome shape is kind of an illusion because we're used to seeing domes now as they look with telescopes in them. But it's not really a dome, it's a spiral staircase with doorways that look out. So it has kind of the familiar dome shape of an observatory, but that's not how it was designed. El Coracal was built by the Maya, and it was designed to observe the planets and the stars. And it represented a true source of power for the Mayan kingdom. There was also Stonehenge and these other ancient monoliths that were built. And those ancient observatories were set up primarily as large instruments. The markers and stones that they set out were lined up by the experts at the time, the high priests or whatever you want to call them, who were looking at the data, and they were using large stone markers or windows and temples to line up with astronomical phenomena. And those were the ancient astronomical instruments. There was even up to Tycho Brahe. Tycho Brahe used large wooden and brass made instruments. One of his famous ones was the Grand Quadrant. And the Grand Quadrant, whenever it was built, it required 40 servants to pick it up and move it and set it up into place whenever they first set it up into place. It was a big object. And so to do his observations, it required the work of several servants during the course of the night to turn and to set up and align his quadrant so that he could make measurements with it. Perhaps that's one reason he stopped using it and moved on to other instruments, but it was very precise when it was operational. Then right after Tycho Brahe's time was Kepler, and contemporary with Kepler was Galileo, and that's when we started seeing telescopes used to look at the sky for the first time. And Galileo's telescope was a refractor. It was a glass lens at the front and a glass lens at the back, and the two combined to make a magnified image of the stars. And really what's going on with magnification is with this glass lens, you're increasing the light gathering ability of your eyes. Your eyes have a pupil at the very center that lets in light, and you can only let in so much light, and it builds an image up on the back of your retina. By increasing the effective pupil size to a disc, like so, then you're getting all of that surface area of that disc able to compound the light that's falling on it and make it form an image at the back of your eye on your retina, even with the use of your pupil in that system. And so you're getting a larger aperture, which is allowing more light in. And the job of a telescope really is to serve as a light bucket. And the more light that you can get in an aperture, the fainter objects you're going to be able to see, because you're gathering more photons of light. And those photons, putting them into focus, you can see fainter objects. One other important thing about a larger aperture is the larger the aperture, the more resolution you get. And resolution is defined by the airy disk of a star. Let's say that you have an image of a star that appears like so, and that you would say is one resolution. If you had one that the image appeared like so, then that would be less resolution. This would be greater resolution because you're getting a smaller, precise picture of a star versus a larger flat disk of a star when you magnify the image to a high degree. So to get that increase in resolution, though, requires an increase in the size of the opening of your aperture. The reason for this was noted by Airy, and it's called the airy disk. And the airy disk is the size of the star image in a picture or to your eyeball whenever you're looking at it, and it's limited by how large or how small of an aperture that you have. And that's how you get resolution. If you want very fine resolution in a photograph of a starry object, like a cloudy nebula, for instance, in order to get that very fine resolution, you have to have a larger aperture to decrease the size of your airy disk, and that's resolution. Today, we have much larger telescopes, and the design has changed from Galileo's day. They had lenses, and they noticed something, though, when they were using the lenses, that the corners of the lens caused something called chromatic aberration. And they've tried various ways to fix that by adding a doublet of glass behind the first lens. You put a second lens, and that allows you to fix this problem. The main root of the problem is that from the corners to the center, your blue light and your red light across the visible spectrum is coming to focus at two different places. So your blue light may be perfectly in focus here, but because the focal length and the wavelength is different, the focal of the image of the red image is coming here. The focus of the red light is coming here, and the blue light is coming here. And so you can never get either the red or the blue perfectly in focus at the same time with a single lens. They added a second lens that counteracted that effect to some degree and lets you focus the light, but it still wasn't perfect. And now, if you wanted to get a perfectly corrected lens, you might have to have a 3 or 4 lens elements in the front of that refractor, 3 or 4 pieces of glass. That also means that you may have on each of those pieces of glass 2 surfaces, and the glass has to be perfectly clear. So you have to machine both sides of the glass times 3 or times 4, and then you have to have perfectly clear glass with a good refractive index. And so to get that, good APO refractors are very expensive. Now, a guy named Newton came along, and he developed the reflecting telescope, and we'll roll some footage in here to compare reflectors and refractors. Back when Galileo was first using his telescope, he had a refractor, and that design is still actually in use today. This is a very lovely Astrotech telescope, and it consists of a glass lens at the front, and you can see the glass there, and it sends the image down this tube, and in this case to a diagonal mirror that reflects it up so that you can focus it into an eyepiece. And it's small, it's compact, you can put it on a tripod, you can take it in a backpack and go camping with it. It's still a very useful telescope, but for comparison's sake, here is a large 10-inch Newtonian reflector. Isaac Newton came along and redesigned the telescope somewhat. He realized with his study of optics that you didn't have to have glass at the front and then focus an image at the back, but you could have the glass at the back and focus the image at the front. One of the problems is, if you look in here, if you look straight in at the mirror in order to get an image, you're going to get your gigantic head in the way, and it doesn't do you much good if you're blocking the light. So wisely, Newton decided to put a second mirror here, the little diagonal mirror. You can just see it there, held in place by some vanes. And that reflects the image out where the eyepiece can get a look at it. And then you can see the mirror image there. And so by that one little trick of sending the image out the side, Newton was able to put the image-making mirror at the back, and then you could use mirrors instead of lenses. Another advantage of mirrors is that for the same light-gathering ability, they're much cheaper to make because a lens has to be clear and perfectly clear and free of bubbles and imperfections, whereas the glass that you use to make a reflector can actually be pretty crude as long as you can create a perfectly smooth surface on it. And you only have to have one surface that you can then coat with a reflective like aluminum or silver or something like that. And you'll get a steady image, whereas with a refracting telescope, you have to do a lot to it to make it clear, and you have to surface multiple glass surfaces on the way through, which drives up the cost. So for the cost and for the larger aperture, a reflector is often a better choice if you're wanting to get at fainter objects. The refractor, though, is still a viable candidate, and lots of people use it because you can pack it up and take it hiking with you. But and one of the good things about a refractor is you can get a really nice image of the planets and some of the brighter objects in the sky, and you can still get a very nice visual look at them. The reflecting telescope is also a lot bigger, and so it's heavier, and you're getting a lot of aperture, but that means that you have to hold that aperture steady in a mechanical way. And it's easier to do that with a lighter weight refractor telescope. So a lot of astrophotographers now still like the smaller refracting telescope because it places less demands on the mount. So why is it so critical to have a mount that's capable of keeping a telescope balanced and working for a long time at once? Why does it have to be such a big hassle? Well, behind me, I have an example image, if you want to call it that I drew on the board. The little blue dots represent stars, and the little brown disk would be Jupiter. In a typical astrophoto, your stars are going to be about 1 to 2 arc seconds big. And Jupiter has an angular size of about 30 arc seconds at times, and it can be up to about 50 arc seconds big. So if you had a telescope that had any kind of decent focal length on it and a camera setup or an eyepiece setup, and you were only getting a 60 times magnification, if your drivetrain that was holding your imaging system together, your mount, if your mount had an error of just 1 arc second, if it just had an error of 1 arc second, that magnifying power of your telescope being 60 times would translate that up to 60 arc seconds of error in your image. And so you'd go from something the size of a typical star in the background of your image to a blur disk the size of Jupiter. And that's only if there was 1 arc second of error in your image while you had the camera shutter open. So it's actually pretty amazing that with modern equipment, you can get something that can hold an image steady for up to 10 to 15 to 20 minutes for a single exposure, although typically you might run exposures of less time than that. But still, you can run 5 to 10 minute exposures, and it will hold a star image on there within the error of what you can see the size of a star being, and it can hold that error down to under an arc second with tracking. And so with a good steady mount with good tracking, it's possible to get the most out of your optics and to get the most out of your CCD camera and actually get star images that are precise and high resolution without them being blurred. And so you can appreciate how much of a job your telescope mount is doing and why focusing the effort and expense on that is so important. All right, so you can see that the reflecting telescope allows you to make a lot bigger aperture for less cost, but the opposite of that is you have a lot more weight. When they started building up big glass discs, they kind of reached their technological limit with Palomar. The giant mirror at Palomar And I'll roll some footage in here of the Palomar Observatory. This is the Palomar Observatory near San Diego, California. And one thing that's very interesting to see is, for reference, the size of the man standing by the door and the entranceway steps compared to the dome and the building required to support the telescope. Inside is this gigantic piece of engineering. The large horseshoe bearing here was balancing the weight on hydraulics, and then it had another bearing down here at the bottom. And again, there's a comparison, and there's a man on the scaffolding. You can see him in relation to get an idea of the size of the mounting required because of the heavy weight of the glass disc. This is where the reflecting mirror would sit, and it required nearly a battleship to keep it steady. The Palomar Observatory was designed around the centerpiece mirror, a 200-inch, which is, I believe, 5 meters. So a 5-meter glass disc. And it was one solid disc, and it was very heavy. And it took them a couple of decades to actually build that machine. And by the time they did, though, it was worth every bit of the effort that it took. But for the time, it was very, very expensive. There's a book, The Perfect Machine, Building the Palomar Telescope, by Ronald Florence. And this is an excellent book if you want to hear about everything that it took to build the Palomar Observatory. It's quite wonderful. All right, so after that, they started finding technological ways to make bigger telescopes. And a good example of that, they built in Hawaii the Gemini North telescope. And it's an 8-meter glass disc, but they were able to reduce the obligations of the mount by reducing the weight to a great degree. And even though it's larger, it weighs less than the Palomar Observatory. And another advance was made when they built the Keck telescope. They built twin 10-meter telescopes, but the advantage that they had there was they made each of those 10-meter telescope mirrors is not one giant mirror. It's actually segmented mirrors, and it's a hexagon of them. And so they have mirror segments, and with computer-controlled motors, they were able to make those segmented mirrors perform like one giant mirror, which is pretty impressive. It allowed them to handle the weight of such a big telescope, but to do it in a way that still gets you the benefit of that gigantic surface to get the very fine resolution. The limit of the refractor was reached by the Yerkes Observatory for the University of Chicago. Gregory Hale had built several large telescopes. One of the famous ones he built was the Lick telescope. The Lick telescope was built in California, right outside of San Francisco, and it was a wonderful, wonderful designed telescope. And you could see from the images of it, it was a very large instrument, but it was not quite big enough for Hale, and he was able to get some larger glass discs, and he convinced another businessman, Yerkes, to build it or to pay for it, and they installed it at the University of Chicago. And that building was also a giant observatory building, but it was kind of the limit for the time of the large refracting telescopes. The other thing that they found was its location on Williams Bay was not ideal. It was foggy at times. You had a lot of humidity by the Great Lakes, and those factors combined to make the seeing, which is the turbulence in the air, really pretty awful. And so when they moved back to California and they built Mount Wilson and they built the Palomar Observatory, they finally got smart and started locating those observatories up on top of mountaintops. And the reason they did that was to get above the air and the turbulence of the air. And the higher you go, the thinner the air is, and the less interference you're going to get from the turbulence. Nowadays, they have been able to overcome this somewhat by using adaptive optics. And what they do is they can either analyze the image, or they can send a laser beam into the sky and analyze a pinpoint that it makes against the air, and see what that image of a laser beam dot is doing up in the air. And they can actually adjust the surface of the mirror to compensate for the effects that they're seeing in the atmosphere. That is a tremendous advantage, but not every ground-based observatory has that. Another way that you can do that, though, is you can get into space, but we'll talk about that here in a minute. Now, when it comes to observing the light that comes in these large telescopes, back in the day, you would just look at the light through an eyepiece, and the astronomer would either sketch or make notes of what he saw. Tycho Brahe used a pair of compasses, and he would use the tips of the compass to measure the distances between stars. And then you also had fine graded brass plates that you could read off, and you could move needles inside the eyepiece, and then below those outside of the eyepiece you could see how far your needles were moved, and so you could read the distance of the angular separation there. But that was back in the day, so to speak. William Herschel was the guy that discovered the planet Uranus, and he was kind of an innovator in building large telescopes. And one of the other innovations that he's known for is being one of the first to experiment with using photographs to take images of stars. Photography had been around for a little while, but it was still pretty young as a technology. But pretty soon he wanted to adapt that technology and use it to take images of stars. And they attempted, I think, to take a picture of the star Vega, but it was some time before they were actually able to make good images. One of the problems was you had to deal with a wet plate of glass to get an image, and you had to specially coat the glass with silver to get it to work. It was just very delicate. They were soon able to move into a dry film on a plate, and that was better. And then even better still, Kodak, the famous camera film company, they made a special film emulsion, especially for photographing distant objects. And what they did is they used special chemical ratios on the film, and they had special techniques to prepare that film. And you would prepare the film, and then you would put it in the camera, use it for your image, and then you had a special process to develop it. And if you did that, then it was sensitive enough in the entire spectrum, including red all the way to blue, and you would get very good color images using that Kodak film. But since that time, when they got to the peak of the development of that, they still realized that film grain had its inherent flaws, and they wanted to do something a little better, and they started using electric detectors. At first, they were using photoelectric detectors to just detect the brightness levels of stars compared to each other, but then they were able to turn those detectors into something called a CCD, or a charge coupled device, or an array of pixels, individual detectors. Each one of those pixels is an individual detector. And by building a square CCD chip, they were able to do the same job that film was doing, but produce it digitally. And at first, these were very low resolution, and they weren't, you couldn't get as much fine detail as you could with the film. But as technology progressed, the technology surpassed film, and now CCDs are pretty much ubiquitous. So you're going to see those in everything that you do. Recently, CMOS, which is another technology for building those image sensors, has kind of won over a few converts for using for astrophotography. In the old days, CMOS was a lot noisier, but just as time continues to march on, the technologies get better, and CMOS detectors are now rivaling CCD detectors. But you're still in observatories, you're going to probably see CCD detectors being the top right now. Now, another technology that they use besides the telescope that is optical in wavelength is they use the radio waves. They discovered whenever they started looking at radar and detecting signals, earthbound signals, they were able to also see signals emanating from the sky. And they could see those radio waves coming in, and they decided, hey, this is an area that we could research that would give us some more information about what's going on, because visible light is just one part of the entire spectrum of the vast electromagnetic spectrum, and radio waves are part of that as well. And so you can look at light in radio waves, and you can actually see stars in radio waves. One of the big advantages of that is that you can look at them during the day, and you can look at them possibly through clouds, because the waves will go through, unlike visual light. But one of the disadvantages is the wavelength of a radio wave is much longer. So in order to get good resolution, you have to have a much bigger collection of aperture and a much bigger disk. And so some of those disks are very large, and it's very, very difficult to use. And you can't even put them on what you would think of as a satellite dish pointing mount. You have to actually make them be fixed in place and let the earth carry them along, and you can't even really move them. You can have a horn antenna that can move up on the dish and point at different areas of the dish to maybe steer the focus somewhat, but it's not near as mobile as an optical telescope. But one thing that they've able to do is make something called an interferometer. Now, you know that radio waves or light waves or any of those, any electromagnetic wave can interfere with each other, and normally you think of interference as being bad, and usually it is, because you have destructive interference. But you can also get two waves that are interfering in phase with each other, and then you get constructive interference, and if you add those two waves together, the resulting wave is better, and so you can get a stronger signal by using constructive interference. And by also being very smart about it, you can slightly modify the locations or the distances where those waves are traveling, and you can use the interference patterns, not only of constructive interference, but just the fact that they're interfering, and you can look at the interfering patterns to deduce more information about the signal. And so you can use something called an interferometer. That would be two dishes, and then you can also make something called an array. An array would be multiple dishes that are stretched out over a space, and so you can use the entire floor of a desert and fill it with radio dishes, and perhaps you've seen pictures like that, famously from the movie Contact, where you have a long stretch out of dishes, and each one of those dishes is located at a pre-calculated point. They're not just spread out random. They're put at those places because the distances between them are going to be used for interferometry, so that you can treat that entire area as one big dish, even though it's made up of individual points that are your dish detectors. Then, besides radio waves and looking at interferometry, there's now observatories that have gotten above our atmosphere. So that's getting even above the air is another way to deal with the seeing problem. You had some observatories that were on top of mountains. Why not go all the way up above the air and go all the way into space? One of the most famous of those is the Hubble Space Telescope. The Hubble Space Telescope was primarily first famous because it was a giant failure. And people now, looking back, don't realize that. But at the time that it was launched, up until it underwent a repair, it was a boondoggle, and they actually laughed at the government for having funded such a monstrosity. What happened was the engineers that were designing it put a very precise figure on the mirror that was in the Hubble telescope, but they were precisely wrong. One of the test fixtures that they used, they were using a new method to test the optical system. Instead of relying on a traditional method, they tried a different one. And the new method would have worked, but the instrument that they built to test it actually had, they think maybe, had a small fleck of paint that got in between one of the lens elements of their test rig. And just that fleck of paint and the thickness of that was amplified greatly when they were looking at the flaws or trying to make the figure of the mirror to go in the telescope. And so the very small error in the test rig resulted in a large error on the telescope mirror. And it was very precisely wrong. Once they discovered what was going on, though, and they figured out what the error was caused by and where it was coming from, since it was such a precise error, they were able to make a precision lens to counteract that. And they actually flew a mission to service the Hubble telescope and famously got up in there into the inner workings, replaced some of these elements, and put this other lens in place, effectively giving the Hubble Space Telescope glasses. And by the use of that corrective optic, they were able to then get very high resolution images. And they also had some techniques that they developed along the way and some technologies. And one of those is called dithering, but that's another point. But the Hubble Space Telescope then started producing wonderful images, and now it's known as one of the great success stories. Along with the Hubble Space Telescope, you've had other telescopes put into space so that they could look in different wavelengths. An example being the Chandra X-ray telescope, named after Chandrasekhar, and the Fermi Gamma Ray Observatory, named after Enrico Fermi. And they were put up there because you could get a better look at the wavelengths that they wanted to see. There was also something called the Integral satellite, and then the Spitzer satellite was looking at infrared radiation. One more was the Kepler satellite, which was looking at visual wavelengths, but its mission was to actually study stars to see if they have planets going around them. And so the Kepler mission was looking for exoplanets. Now, in the future, they hope to put the James Webb telescope up, and it's en route. It's being worked on and being completed, we're told. It's had a lot of delays, and it's had some setbacks, which is not unusual. If you think about what Palomar had to go through to get their telescope mirror operational, it was a world-beating large at the time, and so it had some technical difficulties. And so it's not unusual that the James Webb telescope is also having its difficulties. But because of that, some people are saying we shouldn't be wasting tax money on this, but the fact is it's going to be fantastic. It's going to be a 6-meter dish, and it's actually going to be made of, like the Keck telescope, it's going to be made of hexagons, and those hexagons will be able to be controlled and act like one solid mirror. And so when they get that segmented mirror and unfold it and get it working in space, it's going to be fantastic. Now, the problem is, the reason why it's taking so long is they're putting it out at an orbit that's going to be a very stable gravitational orbit, but not one that's whipping around the Earth all the time. It's going to be out at a different point that is more stable. And so the problem is it's going to be very far away from Earth compared to the orbit of the Hubble telescope. Hubble was reachable with the shuttle, and you could just go up there if you had a problem, and you could swap out some gear and then come back down to Earth. And it was designed to be done that way. And so if it did have a problem, luckily in this case it actually did have a problem, they were able to go up and fix it. But the James Webb is going to be located in a place in space where right now it would be, let's say, inconvenient for astronauts to go up and look at and to fix. And so they want to get it right on the ground and do everything perfect on the ground, because with the amount of money they're having to spend to do it, they don't want it to be a failure. They don't want it to get out there and then break on them. And so, because they're not going to be able to just go out and fix it. So they want to get everything right before they put it up in the air. So let's give these guys a little bit of a break. And even if it takes quite a while to get it launched, it's going to be worth it with the amount of science they're going to be able to do. There's another telescope, the Cherenkov telescope array, that's measuring high energy gamma rays. And it is designed actually to look at much higher levels of gamma rays than the Fermi telescope. And it's like multiple, like an order of magnitude higher. And the reason is it's looking for different energy signals. And so it's a ground-based gamma ray observatory, but it's going to be, it's useful here, and it's not up in space. But it is going to be looking at a different class of objects than the Fermi was looking for. So that's a survey from all the way back from Galileo and Newton, looking at the refractor and the reflector, and then how it's morphed into modern day telescopes for the consumer, and then some of the large observatories that have been made now with the Lick and the Yerkes observatories, and then the Palomar and Mount Wilson observatories, the McDonald Observatory in Texas, some of the ones that are now located down in Chile, the European Southern Observatory, and the Hawaiian Observatory, the Keck twin 10 millimeter discs there. So I hope that you've enjoyed Chapter 6. I hope that gives you enough information to pass your quizzes, because that's what I'm all about. And please join us again next time for another chapter in the Openstax Astronomy textbook. And clear skies, everybody.